In this section, we'll be talking about two fundamental topics. The one topic is inverse trigonometric functions, and the other topic is differentiation. Now, the inverse trig functions we have undertaken, or you have experienced before in your study of trigonometry, so that'll be a review. And the differentiation really kind of follows naturally from some of the things that we've done before. So this is a highly intuitive kind of section. Well, let's review the idea of inverse trig functions, and to begin the idea, let's think about inverse functions generally. When we talked about the inverse of functions, we decided that we can tell whether or not a function has an inverse which is a function. You know, the functions have inverses, but sometimes those inverses are functions and sometimes they're not. And we would like to create a situation with our trig functions where the inverses are functions. Okay, now with regular functions, we can tell if the function has an inverse which is a function by examining its graph. And we said that g, if the function itself is 1-to-1, that is, if for every 1x there's 1y, and for every 1y there's 1x, 1-to-1, it implies that the inverse will be a function. Well, what does this 1-to-1 idea mean? Well, graphically, the interpretation is that the graph will be continually increasing or decreasing throughout its domain. Now, that idea, though, certainly doesn't apply to something like the sine curve. You see, we don't have a situation where we have a continually increasing or decreasing graph, and therefore the inverse of the sine function will not be a function. As a matter of fact, if you think about it, if you take this graph and think about the inverse, it's a reflection in the y equals x line, so you make that reflection and you'd get a squiggly line like this going down the y-axis, you see. Certainly not a desirable situation in terms of our idea of function. It would fail miserably a vertical line test. Well, let's get back to the topic at hand. What we want to do is create a situation where we have a continually increasing or decreasing graph. And to do that, we'll limit the domain of the sine curve, the sine function. Now, we want to, though, contain all of the range values within this limited domain. Now, you know the range goes from -1 to 1. So we want to contain all values from -1 to 1 in that range, and therefore we'll limit the domain of the sine curve to this region, this interval. The interval from -π/2 to π/2. So here's what we're doing. See, so here's the domain then of our sine curve that we can take the inverse of and have a function. So we can talk about the inverse sine function, you see. Now, I think it's important for us to examine several aspects of the situation. Let's consider this in terms of angle measure. If we were thinking about measuring angles and considering triangles and so forth, when we talk about sine as opposite over hypotenuse and such things, consider an angle here in the first quadrant. And here's the angle theta. And as we increase this angle, you see it's opposite over hypotenuse and so on. We know all about that kind of stuff. But the idea is that this is 90 degrees, which is π/2. And this is, if we're thinking about the angle generated in this direction, this is -90 degrees, and this is -π/2. So really, when we're talking about limiting the domain to -π/2 to π/2, we're talking about fourth quadrant and first quadrant angles. That's kind of an important thing to realize, because you know that we should be able to switch from the idea of radian measure to degree measure. And when we make that switch, we have to kind of change our thinking sometimes from one graphical form to another graphical form. Well, let's jump into the idea of creating the inverse here, or generating an inverse. If f of x is sine x, then we know we write that as y equals sine x. And to generate the inverse, we swap the role of x and y. We replace y with x and x with y, and we solve for y. Now, to solve for y, here we have the sine of y. To isolate y, we need to undo that operation of sine. So we need an idea of undo sine. Well, that's the idea of inverse sine or arc sine. So we take arcsine on both sides. Arcsine x then is the arcsine of sine y, you see, would be simply y. So we're undoing that idea of sine. Now we generally write this as y equals arcsine x, and the notation, an alternate notation, is this notation. They mean the same thing. Now remember, this business and this business are exactly the same. Now I took this from up here. I just swapped the sides here so that the y is on the left side on both of these, so that we can see of greater equivalence here. That sine y equals x means precisely the same thing as y equals arcsine x. And a real good interpretation of this is that y is the angle whose sine is x. You see, we're taking the sine of y, so y is the angle whose sine is x. And over here, y is the angle whose sine is x. It's a real good interpretation, comes right from that, of the idea of arcsine, or inverse sine, if you'd like. Now we could use a notation here that f inverse of x, that this is indeed the inverse function of f that we talked about before. Okay, so that's just another notation. Now let's talk about domain and range. We said that at the get-go we were talking about limiting the domain of the sine function. And so the sine function has as its domain negative pi over 2 to pi over 2. And the range is the full range for the sine curve, negative 1 to 1. Now, we know this relationship between function and inverse is the idea that the roles for domain and range are simply swapped. That is, the domain of the function becomes the range of its inverse. The range of the function becomes the domain of the inverse. And so from this domain gives us a range for our inverse, and the range of the original function becomes the domain of our inverse. So nice relationship going back to the stuff that we've talked about before. Okay, so we just generated an inverse function here. And we're going to go through it here for cosine and tangent as well right quick, now that we understand the process. And I invite you to take a look at the inverses for the other three trig functions that are in your textbook. All right, let's talk about cosine. Now the cosine curve looks a lot like the sine curve. We recall it's the same kind of continuing wavy kind of pattern left and right. Now here is one full cycle of the cosine curve from 0 to 2 pi. Now once again, the graph is not continually increasing or decreasing throughout the domain, which would be from negative infinity to positive infinity. So what we have to do is limit the domain. And we want to limit it in such a way that we contain all of the values that are in the range. The range again is from negative 1 to 1. So we limit that domain by going from 0 to simply pi. Now we're just, that limiting of the domain, we're just kind of making it easy on ourselves. We can limit the domain in a lot of different ways in order to accomplish the task at hand. We could choose a different interval over which to limit the domain. We could limit the domain right in here, for example. We could limit it over here, for example, or out there, or out here. But we're trying to make it convenient for us to make the calculation for inverses a little bit later. And so we're trying to relate it in a nice way to angles, angle measure, and so forth. We're trying to use the first quadrant, you see, and stuff like that, because we want it to relate that way. All right, so here we're limiting our domain to 0 to pi, and we know that that's, here's the first quadrant. If we're talking about angle measure in quadrants, this is first quadrant angles, second quadrant angles, so we're talking about first and second quadrant for our definition of the cosine curve. You see, and then when we go to that inverse idea, we have to realize where we are with our original function. All right, the domain 0 to pi, the range negative 1 to 1. All right, we go through the inverse process. Y is cosine x, inverse, swap the role of x and y. Now we take arc cosine on both sides. So arc cosine x is equal to y, or swap them around, y is arc cosine x. Now, y is the angle whose cosine is x. y is the angle whose cosine is x, you see. Direct interpretation from one to the next here. All right, an alternate notation, and the domain and range are swapped from the original function. Similar idea with tangent. Now, here's the tangent curve, recall, and let's see, the domain of the overall function would be basically negative infinity to infinity, but we have some ideas or some items within that domain that have to be omitted. Negative pi over 2, pi over 2, 3 pi over 2, and so on in a prescribed interval. Or in a prescribed pattern, you see, we can limit that. We're not defined at these vertical asymptotes, and we have to say that, I suppose. But to limit the domain here, the logical way to do it for the tangent curve is to limit the domain to negative pi over 2 to pi over 2. So in limiting the domain this way, we are limiting it in a way similar to the sine curve. Remember, the limitation was fourth quadrant, first quadrant, and that's really what we're doing here. Fourth quadrant, first quadrant, you see. So the domain is negative pi over 2 to pi over 2. Notice the strict inequalities here because the function isn't even defined at negative pi over 2 and pi over 2. That's why we need the strict inequalities. Range is from negative infinity to infinity because this graph just exits upper right here as it gets really close to this asymptote, and lower left here as it gets close to this asymptote. So the inverse then, y is tangent x. The inverse, swap the role of x and y. Arctangent on both sides, you see, will undo this tangent idea over here, leaving y. So y is arctangent x. Y then is the inverse tangent of x, just another notation. These are interchangeable parts. And we understand that y is the angle whose tangent is x. Very nice interpretation. And the domain and range values are swapped from the original function, as expected. Suppose we want to evaluate something like this, arcsine negative 1/2. Now, it's important to understand what the request is. We're really asking ourselves, what is the angle whose sine is negative 1/2? We can make the request by making an equation out of this and massaging the equation a little bit. But let's understand that when we're talking about inverse sine or arcsine, the angle that we're looking for is falling within a certain interval because we defined arcsine in a certain way. We limited the domain of the sine curve in order to develop arcsine. And because of that limited domain of our angles, the angle that we're looking for here is going to fall within a certain region. And that region is from negative pi over 2 to pi over 2, or in degree measure from negative 90 degrees to 90 degrees. So when we are making this request or trying to evaluate this, we would say, well, let's set a letter. Let's let a letter be equal to this. And I'm using y here because of the y's here. But y then is arcsine negative 1/2. So now take sine on both sides. Sine of y is negative 1/2. You see, applying sine over here will undo this, and therefore we have negative 1/2. So it's like the sine of what angle is negative 1/2. Now, this may or may not be familiar to you. We should be able to make the calculation here both with and without a calculator in some situations. And to help us with those situations which we can evaluate without the calculator, we a lot of times will want to draw or sketch a little reference triangle. Now, there are two reference triangles that are useful here. So for reference, we would probably write down the triangle that has two 45-degree angles, the right triangle having two 45-degree angles, and remember the sides were 1, 1, and the square root of 2. And then the 30-60 triangle, this one, whose sides are 1, 2, and the square root of 3. Now, these are handy references that you use many, many times probably in trigonometry. So just sketch them on the side, and then we can look at our problem. Oh, we're talking about negative 1/2. Well, the negative idea will put us in a particular quadrant, or will tell us something in just a moment, but the idea of 1/2, the sine of some angle is 1/2. Well, we go back over here and we look at it a little bit. Oh, we have opposite and hypotenuse here, and the angle is 30 degrees. So opposite, hypotenuse, oh, the sine of 30 degrees is 1/2. So we're talking about a 30-degree angle here, and since this is negative, it's negative 30 degrees, or negative pi over 2. Now, I know that it's, let me just get this written in. Excuse me, I said pi over 2, it's negative pi over 6 for 30 degrees. All right, when you think about inverse sine, you're thinking in terms of these two quadrants, you see. It's an angle which falls in one of these two quadrants. And because we have a negative idea here, it was an angle that falls into this fourth quadrant, and the reference angle was 30 degrees, you see, or negative 30 degrees. Let's evaluate arc cosine 0. Now, as soon as we see arc cosine, we think about the possibilities here. That arc cosine can fall within a certain interval of values. It falls within, and because we defined, you see, the inverse cosine as having a limited domain of 0 to pi, you see, then our arc cosine angles are going to fall within that interval. So we're looking for values here that are between 0 and pi, or in degree measure, 0 degrees to 180 degrees. So we set this up as y equals arc cosine 0. Cosine y then equals 0. Take cosine on both sides, you see. Now, the cosine of what angle is 0? Well, gee, that doesn't fall into the categories for our reference triangles here, but we can certainly evaluate it kind of like this. There are several ways. One way is like this. If we're thinking about an angle generated here, and it's the cosine, you see, is the adjacent side over the hypotenuse. And as this angle gets bigger and bigger and bigger and bigger, this side becomes smaller and smaller and smaller. So that adjacent side becomes 0 when we get up to 90 degrees, you see, for the angle. That's a way of evaluating it and finding that the angle is 90 degrees. Another way is to think about the graph of the cosine curve, and we know that that graph does this. Starts at the top of the amplitude and goes down to the bottom of the amplitude, and this is just kind of like half of it, and this is pi. And this is our limited domain, you see. Now, where is 0? Well, 0 is right here. This is at pi over 2. Pi over 2 being 90 degrees. All right, so our answer then for y is either 90 degrees or pi over 2. Here's another one. Arctangent, square root of 3. Now, arctangent, think about how we define that inverse tangent function, you see. We had to limit the domain of the tangent function in order to generate the inverse tangent function. And that limited domain meant that we're limiting those angles to, let's see, the interval was from negative pi over 2 to pi over 2. So we're thinking about that in finding this arctangent. We have to think about this, negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees. Not including the extremes here. But at any rate, we set y equal to this, and then take tangent on both sides. So now the tangent of some angle is the square root of 3. Well, that's one of our handy references. Back over here, we would look around, oh, here's the square root of 3. Let's see, we want an angle whose tangent is the square root of 3. Tangent is opposite over adjacent. Oh yes, so it's 60 degrees is opposite over adjacent, square root of 3 over 1. So we're talking about a 60-degree angle if we're talking about angle measure. So y then is 60 degrees or pi over 3. Here's one we need to do on the calculator. It says evaluate arcsine of 0.3. That doesn't fit any of our references before. Now, it's handy to realize that arcsine can be, the notation for it is sine with this little inverse symbol, you see. So inverse sine of 0.3. So we would enter this into the calculator. It's the second function on sine. You see, for inverse sine, makes sense. And then enter 0.3. And if we're in radian mode, we will get this, 0.3047 approximately. And if we're in degree mode, we get 17.46 approximately. Consider this relationship. Here's a relationship that we already realized. The sine of pi over 6 is 1/2. That means the sine of 30 degrees is 1/2, something we already knew. Now take the inverse, or the arc sine on both sides. So arc sine of this side, arc sine of this side. Arc sine of sine, they kind of offset one another. So 30 degrees then is the arc sine of 1/2. Or pi over 6 is the arc sine of 1/2. Okay, that's fine. Now consider this relationship. We also know from trig, you see, that the sine of 5 pi over 6, which is the same as the sine of 150 degrees, is also 1/2. You see, we're just considering a second quadrant angle. Here's what's going on graphically, and I may be over-explaining it here, and this may be obvious to you, but 150-degree angle is roughly right here, if we're talking about that as our angle. And when we talk about analyzing this using angle measure, we think about this reference angle of 30 degrees, you see. And so we have a 30-60 right triangle here. And so we have the 1, 2 square root of 3 idea. You see, that's a way of thinking about it. And so the sine of this reference angle, the sine of 30 degrees, is opposite over hypotenuse. Oh, that's 1/2. So that's what's going on here. That's the relationship here that we talked about in trig. Now, if we talk about arc sine then, arc sine of sine, you see, would be 150 degrees. But arc sine 1/2 would appear on the right side. But is it true that the arc sine of 1/2 is 150 degrees? Is that true? No, we found over here that the arc sine of 1/2 is 30 degrees, not 150 degrees. And the reason for the discrepancy here has to do with that limiting of the domain when we defined this inverse sine function. You see, so we have to be careful about that relationship as we go on. So here's what we have to realize, that if we're thinking about an arc sine kind of evaluation, the arc sine of the sine of an angle is the angle itself, you see, provided that angle falls within a certain interval, provided that angle is from negative 90 degrees to 90 degrees. Or if we're talking radian measure, then it just means that that angle is between negative pi over 2 and pi over 2. So it's the same idea. Arc sine of sine theta is theta, or arc sine of sine y is y, provided the theta or the y fall within that region, that interval of negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees. And in a similar way, if we're talking about, we have arc sine x, and we take the sine of arc sine x, well, it's like we're taking a function and its inverse here, and they kind of undo one another. Well, we're going to get x, but provided this x falls within a prescribed interval. And that prescribed interval for arc sine, you see, what can we take the arc sine of? Well, how are we limited, you see, in that region over which we can take that arc sine? And it turns out that the x must fall between negative 1 and 1 because of the restrictions on that inverse function that we originally talked about. Here's an equation involving an inverse function. It says arctangent of this expression is pi over 4. Now, a lot of times when you see equations involving either trig functions or inverse trig functions, you can apply sort of the inverse of whatever you see in order to let the equation kind of shake out for you. Here we see the inverse tangent idea, arctangent. So we'll apply tangent on both sides. So we want the tangent of this expression, the tangent of this expression. Now, the tangent of arctangent, they sort of take each other out, so we have 2x minus 3. And then the tangent of pi over 4, pi over 4, that's tangent of 45 degrees if we're thinking in terms of degree measured angles, but that turns out to be 1. And now we simply solve the equation to find x to be 2. Here's a rather interesting one. It involves an inverse, the inverse of sine, and it also involves cosine. It says y is arc sine x, where y is in the first quadrant. And we want to find cosine y. Now remember, y is an angle whose sine is x. That's what this says. And we want the cosine of that angle whose sine is x. So here's what we need to do. We need to think of it kind of like this. We need to start by using that technique I referred to earlier. That is, the sine of y is equal to the sine of this, which would be x. Okay, so sine of y is equal to x. What does that mean? Well, let's think in terms of ratio here. The sine of an angle is equal to x, but we know that the ratio, the sine ratio, is opposite over hypotenuse. And we can think of this as x over 1. So what we can do is just kind of make a little right triangle. And let's use as our angle this angle, let's say. And that angle is y. And if we're thinking ratio here, opposite over hypotenuse would mean, let's see, x over 1. And now we're thinking about, all right, here's our triangle we're referring to, and we want the cosine of that angle. Well, cosine is adjacent over hypotenuse, but what is this? Well, we can find this if we know two sides of a right triangle. We can certainly find the third, and we do that using the Pythagorean relationship. So let's see. See, the hypotenuse is 1, and I'll let this side be the a side. Kind of jam myself a little bit, but that's the a side right there. So it's a squared plus x squared. And now let's see, 1 minus x squared is a squared. So a then is the square root of 1 minus x squared. All right, good. So this side is 1 minus the square root of 1 minus x squared. Now that's telling us that the cosine of y, since the cosine of y is adjacent over hypotenuse, then the cosine of y is this a side over 1, or the square root of 1 minus x squared over 1, or simply the square root of 1 minus x squared. Let's work another one like this. Here we're given that y is arcsecant the square root of 5 over 2. So y is the angle whose secant is the square root of 5 over 2. We want to find the tangent of that angle. Well, we start with the idea of applying secant on both sides, the secant of the left side, the secant of the right side. So these take one another out, and we have the square root of 5 over 2. Now, knowing that secant y is the square root of 5 over 2, and knowing that secant is, well, let's see, it's the reciprocal of cosine, so it turns out to be the hypotenuse over the adjacent side. Now, with that idea, we can form a reference right triangle and think about it like this. Here's y, here's the hypotenuse, and here's the adjacent side, so the square root of 5 over 2. Now we're going to need the third side of our right triangle, so we can go through and find that third side using the Pythagorean theorem, allowing this unknown side to be a, and it's arbitrary whether we let it be a or b. It'll turn out the same either way. But we have, let's see, the hypotenuse is the square root of 5, and that amount is squared. That turns out to be 5. 2 squared is 4 on the right, and subtracting 4 on both sides, we find a squared is 1, so a then is 1. If this side is 1, then we can easily come back over here. We know that the tangent of that angle is opposite over adjacent, and from the perspective of this angle, the opposite side is 1, the adjacent side is 2, so we have 1/2 as the tangent of that angle. Let's talk about derivatives of inverse trig functions. Consider y is arcsine u. Now, u is just some expression, and the alternate notation for this is inverse sine of u. So these mean the same thing. All right, now we want to find y prime, which is the derivative of arc sine u, or the derivative of inverse sine of u. Now, begin this way. Think about this, and now go into the sine idea. That is, take the sine on both sides. So sine y is equal to the sine of arc sine u, which is simply u. Now, we understand about the derivative here. The derivative of sine y is cosine y times y prime, and that's u prime. Now, with a little algebraic manipulation, this becomes really easy. Y prime, then, is u prime over cosine y. But we understand that cosine y, in terms of this angle idea and so forth, right triangle development, it is adjacent over hypotenuse. And so y prime over this fraction means y prime times its reciprocal. Now, what is hypotenuse over adjacent in terms of what we're talking about here? Well, let's go back and think about sine y equals u. Now remember, u is just u over 1, so we can think of it like this in a right triangle form. That's ugly. Okay. So from the perspective of angle y, the opposite side of the hypotenuse is u over understood 1, so it's u over 1. Now we're thinking about ratios of sides. We're going to need the third side here. So we use the Pythagorean relationship. The hypotenuse is 1, so 1 squared is a squared plus u squared, or 1 minus u squared is a squared. A then is the square root of 1 minus u squared. So a, this side, is the square root of 1 minus u squared. So when we talk about hypotenuse over adjacent from the perspective of this angle y, the hypotenuse is 1, the adjacent side is the square root of 1 minus u squared. So the hypotenuse is 1, so u prime times 1 is u prime, and then 1 times the adjacent side means the square root of 1 minus u squared. So here we have y prime is equal to that fraction, which means the derivative of arc sine u is u prime over the square root of 1 minus u squared. Now, the other notation that can be used here is that this is sine, or the inverse sine of u. And this is what, it's a little shorter to write this, and so when I write the group of them up here, I'm going to use this kind of notation. Okay. When we talked about derivatives of trigonometric functions before, we came up with this list. The derivative of sine is cosine times u prime. The derivative of cosine is the negative of sine times u prime, and so on. And looking at them all together here allows us to notice certain patterns and to be able to recall these relatively easily if you just study these just a little bit. All right, we've had these. Now we're developing these. And these come immediately from a little algebraic development, just like the development that we went through for sine over here. So the derivative of inverse sine, you see, is u prime over the square root of 1 minus u squared. And the derivative of cosine u, the cosine of an expression, is the negative of the derivative of the expression over the square root of 1 minus the expression squared. Now notice the similarity between these two. And as we develop the others, notice other similarities. That for tangent and cotangent, notice these two, and notice they differ only in this minus sign you see in the numerator. Just like up here, they differed only by that minus sign in the numerator. And in a similar way, secant and cosecant, that is the derivative of the inverse secant and cosecants, differ in terms of a minus sign only. So it makes it relatively easy to refer back to these and to understand the relationships between the related inverse trig functions. Okay. Now, we could be faced with a problem like this. Suppose we want the derivative of arc sine 2x. Now, at first, you want to refer back to the list. You just want to look at the inverse trig functions, the derivatives of them, just from the list. And they're listed in your textbook, by the way. So we would say, okay, this is u prime over the square root of 1 minus u squared, where u is the expression here. So we're talking about the derivative of 2x for this numerator. The derivative of 2x is just 2. All right, then in the denominator, it's under the radical 1 minus the expression squared. So it's 1 minus 2x squared. And then just evaluate this, and we have 2 over the square root of 1 minus 4x squared. Here's another one. F of x is arctangent the square root of x. We want f prime of x. We understand that the form of f prime of x for the derivative of arctangent is u prime over 1 plus u squared. Now, that comes from the list over to the left. All right, now we go through and we evaluate that. U prime, the derivative of this. Well, we think of this as x to the 1/2. So the derivative is 1/2 x to the negative 1/2. And then in the denominator, 1 plus u squared means 1 plus the square root of x squared. And then we just manipulate this a little bit algebraically. The 1/2, we can think of the 2 appearing in the denominator, and x to the negative 1/2, negative exponent kicks that rascal down to the denominator, and x to the 1/2 in the denominator means the square root of x. So we have 2, the square root of x, times 1 plus x, or x plus 1, in the denominator as factors under a numerator of 1. As you might expect, we're going to put the techniques of derivative of inverse trig functions with our other techniques. And here's a relatively elementary example. If h of x is x arctangent x, then the derivative of h of x, that is h prime of x, is, well, we're using the product rule here. So it's x times the derivative of this, which takes this form, plus the derivative of that factor times arctangent x. And the derivative of x is 1, so 1 times arctangent x for this term. Now, the u prime over 1 plus u squared. U prime, that's the derivative of x, is simply 1, and then this is x squared in this position. And now it's a matter of putting it into some palatable form. X times this fraction means x over 1 plus x squared, then plus arctangent x. Here's another one, and this one involves quite a bit of algebraic manipulation as a possibility. You know, and I want to show you this, not to show you how difficult problems can be, but really just to show you that there are a lot of manipulation opportunities. And if you see an answer in the back of the textbook, or if you see a display on a graphing utility that tells you the derivative, and there are utilities that will take the derivative of this rascal right here. The TI-92, in fact, will do that. But when you see that, you might think, oh, that's totally different than what I have. But then again, it may be the same if you go through a manipulative process. So let me show you what this is all about. All right, first of all, we're going to take the derivative here. We're going to find y prime, and we're taking the derivative of this item and the derivative of this item. We're using the product rule over here. So here we're talking about, let's see, it's the u prime in the numerator over the square root of 1 plus u squared. So we get this. All right, that's fine. Now over here we have, let's see, x times the derivative of this. Now we have to use our rules from before about this. So we're thinking of this as 1 minus x squared to the 1/2 power. So the derivative is 1/2 times this to an exponent 1 less than the 1/2. So it's 1 minus x squared to the negative 1/2. And then times the derivative of the radicand. So that turns out to be negative 2x. All right, now we need to manipulate this a little bit. The next term, though, we'll come down and do that in a second. So we had x times the derivative of this, and that's what this is. And then we have the derivative of x times this. Well, the derivative of x is just 1, so it's 1 times this radical. All right, so that's where we are. And now everything else is just a matter of manipulation. And it turns out that the algebra within the calculus is more difficult than the calculus is. You see, so it's the algebra that could get us into trouble here. All right, let's run through this a little bit. Now we have some cancellation opportunities here and simplification opportunities. This 2 in the denominator and that 2 can cancel. All right, good. We have this x times that x gives the x squared in this numerator. And this minus sign I'm putting right here. All right, that's where all of these things come from. All right, the negative exponent pops this expression into the denominator, and it is this expression to the 1/2 power, or the square root of 1 minus x squared. All right, that's where this comes from, and this just came down. Now, you might think, well, gee, let's just stop right here and consider this as our answer. Well, that would probably be okay in many circumstances. Then again, some teachers might say, well, that's not okay because you have radicals in the denominators or something like that. We need to manipulate a little bit further. And if you looked in the back of a textbook for an answer to this problem, then you probably would not see this expression, and you might think that you made a mistake. But then again, you may not have made a mistake because we can manipulate further. And let's go through and do that. Notice we have common denominators here on these two fractions. So we bring the fractions together by collecting numerators. We have 1 minus x squared over the common denominator. All right, that's where this comes from, and this just came down. All right, now I'm noticing that we have 1 minus x squared here and 1 minus x squared as the radicand in the denominator. Now, that means that we can write this as 1 minus x squared times this to an exponent which is negative 1/2. We're just kicking this up into the numerator. We think of this as 1 minus x squared to the 1/2, kick it up into the numerator, and we have the negative 1/2. All right, fine. Now we have the bases here alike, and the exponents, negative 1/2 and 1. When we multiply like bases, we add the exponents, so this is 1 minus 1/2, which is 1/2. So it's this base to the 1/2 power. All right, we're making a little progress here. So now this, well, let's take this step and continue it up here. All right, this is the same step we had at the bottom over there. All right, let's continue with it. Now this means the square root of this expression, but look at what we have here. Oh, these are alike. So we have two of these things. We're just adding radicals, and they have the same radicand. So we have 2 the square root of 1 minus x squared. A much simpler kind of expression for this derivative than we first may have thought possible.